off last class, we were talking about complex numbers. And it didn't even have much of a tie-in to what we were talking about before that with polynomials, except that very beginning, what happened was we were trying to find, we were trying to write x squared plus 1 in completely factored form, right? So we had this polynomial, trying to write it in factored form, and in order to do it, we had to invent a special number, I. Okay? So we wrote that as x minus I, x plus I. And then we said, okay, now we've invented these special numbers, let's investigate them a little bit. Okay, so the rest of the class was all about just investigating this new number that we invented. And now I'm going to pull it back to polynomials. All right, so this is called the fundamental theorem of algebra. There are 3 fundamental theorems in all of math. There's the fundamental theorem of arithmetic, fundamental theorem of algebra, and the fundamental theorem of calculus. So you now are going to know 2 of the 3 fundamental theorems. So you're making your way up in the world. So the fundamental theorem of algebra is actually the algebraic equivalent of the fundamental theorem of arithmetic. So the fundamental theorem of arithmetic is something you learn like way back. It says that every number, every integer has a unique prime factorization. You can take any number and write it as a product of prime numbers that's different from every other number. So the fundamental theorem of algebra is similar. It says that you can take any polynomial and you can write it as a product of linear factors. So you can write it any number as a product of irreducible things, and you can write any polynomial as a product of irreducible things. So linear factors are the irreducible things here. So I can take any polynomial and write it as in factored form, completely factored form, where each factor has the form x minus one of the zeros. And for a polynomial of degree n, there are going to be n linear factors. And there are going to be n zeros, complex zeros. So there's going to be some that are purely real, some that might have an imaginary part, but n altogether, n complex zeros. All right, so for example, here's a polynomial, x minus 2 cubed, x plus 2 squared times x plus 5 to the 4th. It's a 9th degree polynomial. Okay? And I can tell that because if I write it all out like this, right, I use the exponents. Instead of doing cubed, I write x minus 2 times x minus 2 times x minus 2. Write it all out. Then I will have 9 factors. And if you multiply 9 linear factors together, the highest power on x is going to be a 9. So this is a 9th degree polynomial, which means it has to have 9 zeros. Okay. Some may be complex, right? Some might have an imaginary part, some might not. And we have to count the multiplicities too. So altogether, taking all that into account, 9 zeros. Same as the degree. So we get x equals 2 as a 0, but it's got multiplicity 3. And we get x equals negative 2 as another 0, but it's got multiplicity 2. And we get x equals negative 5, multiplicity 4. So when you count the zeros according to their multiplicity, we end up with 9. 3, 4, 5, 6, 7, 8, 9. So in this case, all the zeros were real, no imaginary part. But we had to count the multiplicities to get the 9. Okay, so here we have a cubic. X cubed minus 4x squared plus 5x. So according to the fundamental theorem of algebra, it's got degree 3, so how many zeros should it have? 3. Yep. So here we have a 3rd degree polynomial. It should have 3 zeros and 3 linear factors. So we're going to find them. So zeros are places where the function equals 0. So I want to solve x cubed minus 4x squared plus 5x equals 0. So in this particular problem, I've been given a little gift. What's the gift? Yeah, there's an x in every factor. So I can pull out an x. And I'm left with x squared minus 4x plus 5. And then this is the gift that just keeps on giving, because this quadratic, what's special about it? It also factors. So I've got x times x minus 4 thank you, x minus 5, x plus 1. And then I have these three factors equal to 0. I can set them each equal to 0. And I get x equals 0, x equals 5, and x equals negative 1. So those are my three zeros. Right? And if I know zeros, I know factors, which I actually already have them here. X, x minus 5, x plus 1. So what was the name of this function? F of x. Okay. So I know f of x can also be factored as x, x minus 5, x plus 1. So degree 3, 3 zeros, 3 factors. Degree n zeros, n factors. Sometimes we have to count the zeros according to their multiplicity, right? If it shows up 3 times, you have to count that as 3 zeros. Sometimes all 3 zeros are unique, right? Sometimes they're not. And sometimes you have zeros that have an imaginary part. So if you have an imaginary zero of the form a plus bi, then its conjugate a minus bi is also a 0. So an easy example of conjugate pairs will be x squared plus 4. It's a polynomial, x squared plus 4. I want to find its zeros. So I say, all right, I'm trying to solve x squared plus 4 equals 0. I move the 4 over. I have x squared equals negative 4. I take the square root of both sides. And what is the square root of negative 4? 2i, plus or minus 2i. All right, so I've got my zeros, which means if I know zeros, I know factors. So I can write x squared plus 4 as the product of 2 linear factors. I knew I was looking for 2 zeros because it was a second degree polynomial, which means I have 2 factors, x minus each of the zeros, x minus 2i and x minus negative 2i. So we get the zeros and the factors. And what happened, I had my 2 zeros. They were complex. They had imaginary parts. They're conjugates of each other, 0 plus 2i and 0 minus 2i. And that will always happen. When you have zeros that have imaginary parts, they always occur in conjugate pairs. Seems like, all right, I'll do some of the exercises with you. It seems too easy. Okay, so one last thing. If you have a negative under a square root, you want to write everything in terms of I before you do any other arithmetic, right? So with real numbers, we have the ability to say the square root of 20 times the square root of 5 is the square root of 20 times 5. Right? You can just smush them together. And then that would be the square root of 100, which is 10, right? But if I wanted to do, if I did this same thing with imaginary numbers, then I would be able to say square root of negative 20 times the square root of negative 5 would be the square root of negative 20 times negative 5, which is the square root of 100, because the negative times the negative makes positive, and you get 10, right? And it just seems like these shouldn't be the same answer, right? You're like, that is weird that they come out the same when these are both imaginary. So this is actually not right. So you can't do this with imaginary numbers. The rule for imaginary numbers is transfer everything to have i's in it before you do arithmetic. Right? So this would be square root of 20i times the square root of 5i. So you take the negative square root of negative 1 out, call it an I. And then this becomes square root of 20 times the square root of 5 times I squared. And we know the square root of 20 times the square root of 5 is 10 from what we did over here with the real stuff. And I squared is negative 1. So we get negative 10, which feels better. Different answer than when you're doing just real numbers. Okay, so we have this polynomials with complex zeros thing. I think I'm going to do a couple of these with you, and then I'll let you try some of the later ones on your own. So my goal is to write each function in completely factored form. I want to write it as a product of linear factors. And I know from the degree how many linear factors I'll be looking for, right? So f of x equals x squared plus 81. How many factors am I looking for? 2. Okay. So remember, if you know zeros, you know factors. And if you know factors, you know zeros. So I'm looking for factors. I want to be able to write x squared plus 81 as a product of 2 linear factors. And they're both going to look like x minus something, right? And those somethings are the zeros of the polynomial. So over here, I might do a little aside where I find the zeros. X squared plus 81 equals 0, and solve. So I get x squared is negative 81, square root both sides, and I get plus or minus what? Square root of negative 81? 9i. Good. So then I'd come back over here and I'd say x minus one of my zeros, which is 9i, and x minus negative 9i, which gives me x plus 9i. So there is my polynomial in completely factored form. And you can always FOIL it out. You can always multiply everything out again to check your work. And let me show you another nifty way to check your work. Because your graphing calculator has a button for I on it. I think this will work. All right, so I'm going to put in the left side of my equation, x squared plus 81, in y1. And in y2, put the factored form. They should be the same, right? If they're equal, the two graphs should be the same. So I'm going to do x minus 9, and then I is the second function over the decimal point. Second I times x plus 9i. And then when I graph these two, I'm going to graph y2 in bold. A little diagonal line next to y2. If you put the cursor on it and press enter, you can change it to a bold. So graph both of these, and they should be the same graph. If they're the same graph, I know that they are in fact equal, and I did it right. So I got to think about my window here. X squared plus 81. It's like x squared, but shifted up 81 units. So -10 to 10 might be good for x, but for y, I have to go up 81 units to see anything. So maybe I'll go like 75 to 95, something like that. Oh, it didn't graph my other one. Maybe you can't do it. Oh, yeah, it's giving me errors. I guess your graphing calculator is not as good as I thought it was. That's too bad. Oh well. All right, that's okay. Okay, so g of x, 2x squared minus 8x plus 9. How many factors am I looking for? 2. And my leading coefficient is a 2. So when I factor this, I'm going to write it as 2 times my 2 linear factors, x minus something, and my 2 somethings are the zeros. And I have to keep that leading coefficient, because if it wasn't there, when I FOIL everything out, my leading term would be x squared, and I want it to be 2x squared. So I just put that 2 in front. All right, so now I'm looking for the zeros. If I know the zeros, I know the factors. So over here, I look for zeros. 2x squared minus 8x plus 9 equals 0. And I would solve that using the quadratic formula. Yeah. So I get x equals -b plus or minus the square root of b squared minus 4 times a times c all over 2a. So that's 64 minus 72, which is 8. Is that right? -8? 8, yeah. So this is 8 plus or minus square root of 8i over 4. So I've got 2 zeros. 8 plus root 8i over 4 and 8 minus root 8i over 4. So I take those 2 zeros, plop them back in. 8, so x minus 8 plus radical 8i over 4 and 8 minus radical 8i over 4. So yeah, go back to when you know factors, you know zeros, because if you have some polynomial p of x, right, and you're trying to set it equal to 0 and solve, if you can factor p of x, then you can get the zeros because you take each factor and set it to 0, right? Right. So if I get like x equals 2, right, x equals 3, x equals -4, whatever I get for my zeros, to go backwards, if x equals 2, then what was in these parentheses had to have been x minus 2. And this had to have been x minus 3. And this had to have been x minus -4, or x plus 4. So you always write it as x minus, and then if the 0 is negative, it ends up becoming a plus, because it's minus a negative. I mean, that's how I do it. You could just leave the sign blank until you know if it's going to be a minus or a plus, but okay. So let's say I didn't. Let's say I found the two zeros of my polynomial, and that means my linear factors are x minus this zero and x minus this zero. If I multiply those two guys back together, let's do that. I think that might be a good exercise. So I'm going to multiply those back together and see what I get. Okay, so I'm going to FOIL. First, I get x squared. Outer, I get minus x times 8 minus root 8I over 4. Inner, I get plus, nope, minus, sorry, minus x times 8 plus root 8I over 4. And then last, that's going to end up being plus because it's negative times a negative. This number times this number. And when I multiply them out, maybe I'll just write it out for now. 8 plus root 8I over 4 times 8 minus root 8I over 4. All right, so this is a mess, right? But when I simplify everything, it's going to get cleaner. Okay, so I have x squared minus 8x minus x root 8I all over 4. That's a plus because I have a minus here and a minus here. So it becomes a plus. And then I have minus 8x minus x root 8I all over 4 plus, now I have to multiply these two things together and I get 64. 8 times 8 is 64. My outer and my inners cancel. They're both 8 root 8I, but one of them is positive and one of them is negative. And then for the last part, I get root 8 times root 8, which is 8 times I squared. So I have negative 8, because this is positive, this is negative. So I have negative 8 times I squared, which is positive 8. Is that okay? Foiling those two together? All right. I'm going to divide my 4 into each piece here. So I have x squared minus 2x plus 1/4 x root 8I minus 2x minus 1/4 x root 8I plus 2. And then, happy day, those two terms are the same, but one's positive and one's negative. And I end up with x squared minus 4x plus 2. Right? Yeah. Is that my original polynomial? No. squared minus 4x plus 2. Y should be not 2. What did I mess up? So when I was foiling these two, I had 8 times 8, which is 64, and I forgot about it, right? My outer inner canceled, and then I did the last, and I got negative 8i squared, which is positive 8, and I had to add that to the 64. So 64 plus 8 is 72 over 4. And then 72 over 4 is 18? Yeah, 18. That's still not right. Because it's supposed to... The 2x. 4.5. I should get 4.5. I'm hoping that would come out to 4.5. Oh my God, you get so embroiled in the complicated stuff with the i's that you forget how to multiply two fractions. Okay. So the problem was over here. I made 2 mistakes multiplying these two fractions. The numerator comes out to 72, and the denominator is 16. Because multiply two fractions, multiply the tops and the bottoms. 72 over 16 is 4.5. Okay. There we go. So this is not the original polynomial, right? But it is only off by a factor of 2. If I throw a 2 in front of this thing, I would get 2x squared minus 8x plus 9, which is the original. Yeah, so all I have to do is throw a 2 in front of my two linear factors, and I got it.
So why was you at the beginning going like take the 2 out and then put just the x squared minus 4x plus 5 to 0?
You could. It would be the same. So think of it like, why would they be the same? So if I have okay, so there's a function. Okay, so there's my function. How do I find its zeros in general? Set it to 0. Okay, so I have x minus 4. So we get x minus 4 squared equals 16. So x minus 4 is plus or minus 4. So x equals 4 plus 4 is 8, or negative 4 plus 4 is 0. 2 zeros at 8, and it's 0. If I take this whole function and throw a 2 in front of it, that's like a vertical stretch, right? So y equals 2 times this whole thing. Causing a vertical stretch of that function by a factor of 2. Now when I set this thing equal to 0, the 2 is irrelevant, right? Because I can just divide both sides by 2, and I'm setting that to 0. So there's two Yeah, and vertical stretches don't affect x-intercepts because a vertical stretch, what was it, 8 and 0? 0 and 8. A vertical stretch takes every y coordinate and doubles it, vertical stretch by a factor of 2, and your y coordinates of x-intercepts are 0. So a vertical stretch by a factor of 2 isn't going to change the zeros. Isn't going to change the x-intercepts. Or think of it, when you write this equation equals 0, I could divide both sides by 2, and I would get x squared minus 4x plus 4.5 equals 0, which is an equivalent equation. So solving this one and solving the one you suggested are the same. So you can do it either way. All right. Let's take a look at C. So I have x cubed minus 3x plus 52. How many factors am I looking for? 3. So I want to be able to write h of x equals a triple bubble. X minus, x minus, x minus. And each of those things that I'm going to put in the bubble are zeros, places where the function equals 0. So the hint is to find one factor graphically, because once you get higher than degree 2, finding zeros gets harder, right? So sometimes you're lucky and you can factor it because maybe there's an x in every term, or there are other tricky things you can do like factor by grouping. But if you have no little tricks, if you're not lucky, the next thing you can resort to is trying to find a 0 graphically. So we go to our calculator and we put in x cubed minus 3x plus 52, and I'm just going to zoom 6 because I don't really know what it looks like. And I lucked out. There's 1 0 right in the viewing window. It looks like it goes right through 1, 2, 3, -4. I can check using the table. Type in -4, and I'm hoping to see what? 0. So -4 is a 0. Okay, so graphically, -4 is a 0. So here's my aside here. So if I know that -4 is a 0, what do I know as a factor? X plus 4. Because I've got this minus -4. All right, so then I'm going to find the other two. Well, if I know x plus 4 is a factor, I could find the other factor. I could find what these two things are multiplied together by dividing, right? Do polynomial long division. So I'm going to do x cubed plus 0x squared minus 3x plus 52. And divide that by x plus 4. So notice I wrote down the 0x squared. If we're going to do polynomial long division analogous to long division with regular numbers, in regular numbers, if you don't have a number in, say, the hundreds place, right? If you don't have any hundreds, you put a 0 there as a placeholder. In order for this to match what we do with regular numbers, you have to have that placeholder. Otherwise, things get all messed up. All right, so remember, you ask yourself, what do you multiply x by to get x cubed? X squared. So we put that over the x squared column. And then you multiply x squared times x plus 4. And you distribute it. X squared times x gives you x cubed. x squared times 4 is 4x squared. And then you subtract. So I have x cubed minus x cubed. Those go away. Then I have no x squareds minus 4x squareds, which is negative 4x squared. And then you bring down the minus 3x. Then you repeat. Go back to the beginning. What do you multiply x by to make negative 4x squared? Negative 4x. Then you multiply your negative 4x times your x plus 4. Distribute it to both terms. Negative 4x times x is negative 4x squared. Negative 4x times 4 is negative 16x. And you subtract. Okay, so I have negative 4x squared minus negative 4x squared. Those cancel. Then I have negative 3x minus negative 16x. So that's really negative 3x plus 16x, which is 13x. Bring down the 52 and start again. X times what gives you 13x? 13, so I put a plus 13 here. And then multiply the 13 times the x plus 4. 13 times x is 13x. 13 times 4 is 52. Subtract. And you get 0. So we're done. No remainder. I have now factored this third degree polynomial. I knew one factor and I got the other by division. X squared minus 4x plus 13. All right, almost there. X squared minus 4x plus 13. This is so I've kind of factored it. I knew x plus 4 was a factor, and I found another factor by division, but it's not a linear factor, right? But can I break this quadratic down into two linear factors? Yeah, I can do that if I find its zeros. I'll just stick them right there. So I have to find the zeros of x squared minus 4x plus 13. It doesn't factor, so I use the quadratic formula. So that's going to be 4 plus or minus 16 minus 52, which is negative 36. Oh, I love when it comes out like a perfect square. So this is 4 plus or minus 6i over 2, which is 2 plus or minus 3i. Divide the 2 into both pieces. So those are my other two zeros. They go in the empty bubbles 2 slides earlier. 2 plus or minus 3i. So I've got 2 plus 3i and 2 minus 3i. Okay. I'm going to let you try D. So it's fourth degree. You're looking for how many factors? 4. Okay. Pick and choose techniques that we've used so far. Follow the hint if you want. See if you can come up with the 4 linear factors.